Hello students, this is equilibrium acids and bases, and we're now going to do some weak acid calculations. Last time we did strong acids, now we're doing weak. Okay, there's our outcomes, our objectives, and you'll see this is ice tables. We're going to use ice. Okay, so quick review. Weak acids form an equilibrium system in water, but strong ones are quantitative, 100%. Here's what I mean. If I take HCl, drop it in water, it splits up, and if I had 100 HCls, they would 100% turn into H positives or H3O positives. So in the beaker, that's all we see is H3O positive. Whereas with weak acids, I have an initial concentration of 100, and when I throw those into water, only say 2% of them turn into products. The rest go back to reactants. So look at my beaker. Instead of having a whole bunch of H positive ions, all I have is, what I mostly have is CH3COOH. Okay? So very few of those reactants actually turn into the hydronium ion or the H positive ion. Okay? Remember, hydronium, H3O positive, and H positive are synonyms in chemistry, same thing. Okay, so a strong acid would be like a pH of 1. A weak acid has a higher pH because there's way fewer H positives in the beaker. Okay, so let's talk about weak acids and Kas, for example. So in our data book, they give us this Ka, and Ka is still products over reactants. And when we have something that produces an H3O positive ion, we could calculate its Ka, or in the data book, it's given to us. Okay. Now the Kb values, because every beaker has H positives and OH negatives in it, there's a little bit of base as well. The Kb value can be found by using this formula. They didn't give it to us in our data book. We have to calculate it. So Ka times Kb equals Kw. So if I want to find Kb, I just take Kw, which is a constant, 1.00 times 10 to the negative 14, divided by Ka, and there I found my Kb. Okay? All right, so let's try an example. Determine the conjugate base of butanoic acid and calculate its Kb. Well, butanoic acid is that, but the base is that one. That's the conjugate base. So there's my Ka. So I take the Kb of that, I'm going to calculate the Kb of that, which is 6.7 times 10 to the negative 10. That goes there. And I know what my conjugate base is. It's just not the acid, right? It's the... I can't even see what that says. C3H7COO negative. Okay, so that's the conjugate base. All right, good. Write an equilibrium expression for the conjugate base of hypochlorous acid. Okay, so hypochlorous acid is HOCl, but the base would be having the proton removed. So OCl negative, throw it in water, makes and then the water gives up its H, its proton, and forms HOCl and hydroxide. Okay, I want to find Kb, so I take my products over my reactants, and there's my expression. I could also, that's just to find the equilibrium expression. The first part of the sentence was write an equilibrium expression, which is hydroxide times HOCl divided by OCl negative. And then if I was to find the Kb, I use my formula, take my constant divided by the Ka, 4.0 times 10 to the negative 8, and I get 2.5 times 10 to the negative 7. Okay, now here's the heart of the lesson right here. If they said, what is the pH of 0.100 moles per liter acetic acid? Well, first of all, it's a weak acid. It's not one of those strong ones. If it's strong, I could just required over given, negative log, done. But this is weak, so I'm going to have to use ice. So I'm going to set up my reaction. I take the vinegar plus water, makes hydronium, and then the acetate ion. And then I start with my ice table. So they gave me one number. It's going to be my initial number right there. I know eventually I want to find the pH, so I just need to do negative log of H positive, but that has to be an equilibrium number, so I've got to do my ice table first. Okay, I know those are 0. Now here's something new. We're going to let X equal the change. So I'm going to put X in there. Then I can go X times by required over given, or 1 over 1, will give me that X, and that X, and that X, and 0.100 minus X. So now I've got my ice table. Okay, now, normally I would go Kc equals products over reactants, but because this has produced hydronium ions, I can go Ka equals products over reactants. And products, I also know the Ka, it's in the data book. I go look it up in the data book for acetic acid, and it's 1.8 times 10 to the negative 5 equals x squared over 0.10 minus x. And then in this class, we will always ignore minus x. The government allows us to do that. So minus x is ignored because it's so small, it's negligible. Okay, so now this calculation's a lot easier. I don't have to use the quadratic equation. So I multiply 0.100 over to 1.8 times 10 to the negative 5, square root it to get x, and I get that number, which is right there. That's the number I care about because that's the number I plug into negative log, the hydronium. Remember, I have to plug that number in because it's an equilibrium number. And I negative log that, and I get a pH of 2.87. Okay, now sometimes they're going to make us calculate the percent ionization. Remember earlier in the lesson I said strong acids break up 100%, but like a weak acid only might break up like 2%. That's what this helps us calculate. So we take this number at equilibrium, hydronium at equilibrium, divided by the initial number, initial concentration, times by 100 to make a percent, and it's 1.34%, which means this reaction only goes 1.34% forward. The rest of it is backward. That's why it's weak. And then I could do my Kb. Kb equals Kw over AA, or Ka. So 1 times 10 negative 14 over the 1.8 times 10 negative 5. And I get my Kb. Okay, perfect. I've just talked about this. This is why we can ignore minus x. If you read the bottom of the table, there's a big long sentence, but it basically says ignore minus x. I've talked about percent ionization already. It's the concentration of H3O at equilibrium divided by initial times by 100. Okay, we've done that already. Sometimes you might have a hypothetical acid. So all acids have an H on them, and then if they just said you have a hypothetical acid, just take some random molecule and we'll just throw an H on it. So we just symbolize it this way. We just say it's HX. So HX, chuck it in water and throw away the proton, becomes H3O positive and X negative. Okay, that's your formula when dealing, or your balanced equation when dealing with hypothetical acids. Okay, thank you very much. See you later. Good luck.